Okay, so as an illustration of the advantages of an orthogonal set of polynomials, or orthogonal set of vectors, which I copied over here, we'll solve a decomposition problem. It won't show the advantage from the point of view of doing the calculation by hand. In fact, you may find that it's more complicated. Well, it's often the case that when you've devised a certain method, when you do it by hand, it actually becomes much more complicated. But the idea is when the machine does it, it's much faster. Just think of the fast Fourier transform. There's something you would never want to do by hand, yet it's a tremendous numerical tool. But even more importantly, it's the concept. So there are so many things where the concept is very, very useful for developing other things, even though it doesn't yield an efficient practical method. So maybe here we won't have the most efficient practical method, but you'll see the concept. And that right now is the most important part. So I'm not advocating that what I'm about to do is easier by hand, but it's a powerful concept. So I'll leave it at that. So first, let's solve this problem the old way. How would we decompose this polynomial p, x squared plus 2x, with respect to this basis? So maybe I'll write it like this. P, don't even remember the notation we use. P sub L, with respect to polynomial L, basis L, equals 3 numbers. And this is actually a classical treasure hunt basis, where you would say that, well, I must have exactly one of this guy, because that's my only source of x squared. So I'm just going to take one of this. And given that I've taken one of this, now I have minus 1/3. I must take plus 1/3 of the first one, and 2 of the second to match the x. Complicated? No, but that's not the point. Did I start recording? I never stopped recording. All right. Now let's do it by the dot product. And we'll see that we'll get these coefficients one by one, which, if you think about it conceptually, is already an advantage over the treasure hunt. Because when you do the treasure hunt approach, you find one, then another, and every next one is more complicated than the one before because it involves more vectors that you have to remember, more numbers that you have to remember, and so forth. The dot product decomposition by the dot product, because the vectors are orthogonal, gives them to you one at a time. So if you only needed one and not all three, and not all n, you could just get one. Do you see all of the conceptual advantages? Well, the formula is, let's go for alpha 1. What we have to do is dot p with, what are we calling it? E1, E2, E3. P dotted with E1 divided by E1 dotted with E1. That's the formula, right? That just picks out alpha 1. This equals divided by what we already know. E1 dotted with E1, 2. So let's see, can we do this? 2/3 dx. 2/3. Because x squared will give us 2/3, and this is an odd function. So 2/3 divided by 2 is 1/3. Cause for celebration? Yes, because it's 1/3. Right? We didn't have to use any treasure hunt logic, any logic at all. That's the power of the dot product. Equals 1/3. This is so enjoyable, I want to do all three. Alpha 2, skipping this, divided by 2/3. No, x dotted with x. We already know what that is. It's 2/3. Divided by 2/3. Okay, let's see what happens here. It's x cubed. 0 because it's odd. And 2x squared. So x squared gives you 2/3, 4/3. 4/3 divided by 2/3. make me tap again. 2. Do you see? Is it magic? It's not magic, but I think it maybe brings everything we've talked about until now kind of full circle, because you see it working. Now guys, I think the biggest question when you first encounter inner products is why. Not what, not how. All of those are straightforward, but why? And this gives you a glimpse of why. And of course, then you'll get to a point where you don't even remember the time when you didn't know that inner products are one of the most important concepts in mathematics. Alpha 3. And that, of course, is 1. Will you let me get away with it?
No.
Without doing the integrals? Yeah. I'm just trying to think real fast of a quick way of doing it. Seeing at least one of them, but I can't without multiplying it out. Well, let's fake it. On the bottom here, we'll have x to the 4th, which is 2/5. 2/5 minus 2/3 x squared, which is 4/3, forget it. 2/5 plus 4/3 minus plus 2/3, I'm not doing it, equals 1. Isn't that amazing? How it worked out?
Wow.
That's right. Okay. Okay, so that's the power of the inner product. Now I will tell you why this basis is terrible and this basis is great. And I could have explained it before, and I think I did on an intuitive level, but this will show you that orthogonality is actually the key.